Hi everyone, my name is Jingwei and I'm currently a job market candidate at UCLA Anderson. And I'm grateful to the award committee for having me as a finalist. And in this video, I'm going to present my recent work on bike lane planning with data. And this is joint work with Zhang from Rockman and my advisor, Ouyang Siddiq. As a quick intro to the motivation, many major cities are expanding their bike lane network during the COVID because they want to create safer road conditions for the increasing cyclist population. And they also want to further promote cycling ridership while reducing traffic congestion. For example, many European cities have invested billions of euros to install hundreds of miles of new bike lanes. And also in the US, major cities such as Chicago and New York City are announcing their bike lane expansion plans as well. And such plans are encouraged by more federal investment from last year. So one natural question would be, do bike lanes really reduce congestion? Is it possible that bike lane could worsen congestion? One common reason for opposition is that building bike lanes can necessarily reduce the space of vehicle lanes, and that could lead to more traffic congestion. But the advocates would say if we build bike lanes smartly, then the traffic congestion will be alleviated, anticipated by most shift from driving to other transportation modes. To that end, the key research question of our paper is where to build bike lanes to promote cycling ridership while mitigating congestion effects. Currently, cities are building bike lanes in a heuristic way by identifying places where ridership is high and where more people live. And to the best of our knowledge, there is no existing systematic and data-driven method considering both network effect and congestion effects. And to fill that gap, we propose a systematic method that first estimates necessary model parameters and then optimize for the bike lane location. Specifically, in the estimation part, we aim to estimate the traffic equilibrium model parameters from data and also predict driving time. And then we aim to find the optimal bike lane location to maximize cycling ridership subject to budget constraint and a congestion tolerance constraint. And also reinforce traffic equilibrium to be satisfied. So I want to mention that our model choice is actually informed and supported by conversations with city planners in Department of Transportation in Chicago and also Transportation Division in Vancouver. Then after setting up both estimation and optimization framework, then we come to we conducted a case study in the city of Chicago. So to spoil some of our empirical results, in the driving time prediction part, our out-of-sample mean error is around 1.3 minutes. And we also find that by adding even 25 miles of new bike lanes can theoretically lift cycling mode share from 4% to 7%. And also in that case, the driving time is increased by at most 7.5% over all driving times. And this is the end of the movie, but not the end of my talk, because we will see how we reach the happy ending. So we've been talking about traffic equilibrium all the time. So what is it? Considering daily commute, the consumers can choose to drive, to cycle, or to take an outside option. The existence of bike lane encourages cycling and reduce driving demand, and then reduce road congestion. But the existence of bike lanes could also increase road congestion because it necessarily reduces the capacity of the road and lead to more traffic driving times. And then the road congestion level can influence driving behavior via the driving time. And here, the road congestion is endogenous because the driving demand can also in turn contribute to road congestion. So we assume that the driver's behavior here in choosing their driving path follows the classic wardrobe equilibrium. That means in equilibrium, contingent on the current congestion level, the drivers are all on their fastest possible route. And then to estimate the model parameters for applying our model framework in any real-world road network, there are essentially two sets of parameters we are concerned about. The driving time parameters theta in the wardrobe equilibrium part, and the MNL parameters beta in the mode choice part. And we shall first estimate theta and then plug in the predicted driving time to estimate beta. Specifically, in the first stage estimation, we aim to solve the following wardrobe least square problem, where we minimize the difference between the theoretical traffic equilibrium traffic flow and the observed traffic flow, subject to the wardrobe equilibrium constraints. And our proposed estimator, theta hat, is the minimizer of the loss function L over all possible values of theta. And we found that our estimator takes the form of an inverse optimization problem. And we strived to show that it is statistically consistent. And that means our estimator can provably recovers the ground truth data generating parameters. And then in the optimization part, everything is tractable except for the traffic equilibrium constraint. And it is composed of the mode choice part and a wardrobe equilibrium part. And by just eyeballing, both parts are highly nonlinear and non-convex. But luckily, we found that the solution to the traffic equilibrium happens to be the unique solution to a nonlinear convex program problem. And so we can replace the traffic equilibrium constraint with the convex program we described before. And then we can transfer the biplane planning optimization problem as a bi-level programming problem, which is known to be hard to solve, especially when the low-level problem is nonlinear. To that end, we solved this optimization problem using a linear approximation procedure, and we showed the suboptimality gap is guaranteed. And next, let's take a look at our case study in Chicago. We were actually able to get every single data from 7 different data sources in the city of Chicago. We built up our own road network and identify the existing bike lane locations, pin down all the origin destination pairs, and obtain the driving routes and biking routes. For the sake of first stage estimation, we were able to get the data on free flow driving time, the road segment geometry data, and also the traffic flow observation. And for the sake of second stage estimation, we were able to get the total OD commute demand and the mode share demand for driving and cycling. And it's worth mentioning that we also obtained the taxi trip duration to evaluate the performance of our travel time prediction. And as a result, to evaluate the performance of our prescribed bike lane locations, we found that in the downtown area of Chicago, by adding optimal 25 miles of bike lanes, can increase cycling share by 3% from 4% to 7%. And also the resulting bikeways can first close the gaps in the existing bike lane network, for example, the bike lane 1 here, and also bridge distant parallel bike lanes, for example, bike lane 2 here. And as for the congestion level, we find that the prescribed optimal bike lane locations can reduce the total commute driving time by 4%. And on road segment level, in the map to the left, we use the color green, yellow, and red to highlight the road segments with less, equal, and more driving time. And so we find that on the roads with new bike lanes, where we would expect more driving time, 8% of them are having less driving time. And on the roads without new bike lanes, 40% of them are having less driving time. So we conclude that the bike lane addition actually reduces congestion in many road segments. And with that, I'm ending my talk today. And if you are interested in more of my work, please scan this QR code to browse my website. Thank you.